This paper asks a terrifying question about non-local decoding, the kind that shows up in quantum copy protection and unclonable encryption. Picture a dealer who takes a random string X in F2 to the n, then splits it into two non-communicating quantum shares, one for Bob and one for Charlie. Bob and Charlie can't swap information. They only get a shared random challenge R, chosen uniformly at random. Their job is simple to state but brutal to achieve. They must output the same parity bit, the inner product of R with X, written as Rx. Now here's the baseline. Even if they're allowed to be clever, the best guess success rate is exactly 1/2. Think of it like flipping a fair coin to predict a bit. If you beat that by a noticeable amount, you're doing more than luck. The non-local search to decision reduction asks, how can they beat the coin toss without secretly reconstructing X itself? The paper proves an information theoretic limit. If Bob and Charlie can both predict the same parity challenge with probability noticeably better than 1/2, then automatically it forces a second property. There must also exist local measurements where Bob and Charlie both recover the full hidden string X with non-negligible probability in essentially the same setting. So parity prediction can't be too good unless full string recovery is lurking underneath. The authors relate this to the classical Goldreich-Levin theorem, where predicting random inner products lets you reconstruct the hidden string. Here the twist is non-locality, meaning they predict together without communication, using only their separate quantum shares and shared randomness. And crucially, the proof doesn't div an efficient extractor. It's not a recipe, it's a boundary line drawn by information theory. If you found this idea wild, smash like, subscribe, and comment parity if you want a part 2 that unpacks the math bound and why those strange exponents appear.